Hi folks, I'm back and making this video to help with the following problems here, 14, 15, and 21 on your homework. Alright, so let's see, number 14 it says, an electric eel can generate 116 volts and zero point 0.2 amp shock for stunning its prey. And again, your numbers on your homework might be different. So that 116, that's a voltage, 116 volts. And then this 0.2A stands for amps, that's an electrical current. Power output. So power in electrical circuits is calculated several ways. One way is current times voltage. Another way is current squared times resistance. Either one. So as I look at this, we're given a current and we're given a voltage. So the product of two is the power. That one's pretty simple, pretty short question. So let me get rid of this and we'll talk about the next one. All right, 15, and there's a picture that goes with 15. I want to take a little bit and chat about that picture. So I'm going to sketch it. Okay, so this symbol just represents the voltage. Now, the first thing you may realize, or you may ask yourself, is why does it not look like this? All right, and the reason is this symbol represents what's a DC voltage, like a voltage source for a battery. The wall outlet provides what's called an AC voltage, and that's a voltage that goes back and forth sinusoidally. And we're going to talk about that in one of the other units later on when we start talking about after we talk about magnetism. We'll talk about AC voltage. But for now, for this video, I'm just going to say that these are equivalent. This is the voltage, and then this circuit right here says it's got a 20 amp fuse. This is just a symbol for the fuse. It doesn't have anything to do with really the physics of the problem, like there's no resistance here or voltage drop across here. And then there's these wall outlets. Here's one of them here, one of them here, and it's got, you know, maybe a bigger one, and one like this. Okay, so, and I don't need all of the detail, but you know, there's the places we plug these in. All right, so there's our, oops, and then this is connected like so. All right, it says what maximum total power can be supplied by these outlets without blowing the fuse. Now, an important thing to realize, again, I like to color code my potentials. This is all conducting material up all the way through here. So this is, I'm going to color code this in red, 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 and believe it or not, okay, if I actually kind of dig into here, these guys would be red, 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 red. And then again, the black is all one potential on the other side. So what happens is when we plug something in, like right here, one side of the plug is at one potential, the other side is at another, and that's what drives a current, makes the thing work. Now, to answer this question, let's see, what maximum power can be supplied by the outlet without blowing the fuse? So what they're asking is basically this: how much power can we supply over here without this current hitting 20 amps? I don't see that there's any reason to look at these individually here. We'll just think of this kind of as the whole here. And power can be written several ways. Oops. You know, one is current times voltage, another is I squared R. Well, the voltage across every one of these we know, right? Red to black, red to black, red to black, red to black. That's the 120 volts listed in, oh, I'm sorry, not 120. Mine says 220. 220 volts. So that's going to be the voltage here. We're going to put that value in. And then the maximum current in this problem is 20 amps. So the 20 amps is going to go here, and then you can calculate the power. So that's pretty much that. Oh, wait, nope, there's a part B. Let's see. Now, when we get that power, it says how many 220 watt appliances can be plugged in without blowing the fuse. Well, without me actually solving it, oh, hold on one moment, I've got to remove my headpiece here. Okay, sorry about that. Without actually solving the problem, let me just kind of go through a quick example here. Let me say, for the sake of example, that this power comes out to be, you know, 2,500 watts. Now, again, it's not going to, unless it's an extraordinary coincidence. I'm just saying kind of what if. And then let's say I had, you know, a 1,000 watt appliance. So if I plugged one of these in, it would draw 1,000 watts and I'd be fine. If I plugged two of these in, it would draw 2,000 watts, and again, we would be fine. But as soon as we plug three of them in, we would have a 3,000 watt draw, and that's going to put that current over the 20 amps. You know, this, in my example here, that 2,500 was a theoretical maximum. So anyway, that's how you work that problem. If this number is less than the wattage given, you can't plug any of them in. You know, in my example, they gave 2,200 watts. Again, I'm looking at part B. So, you know, if, for example, this calculated power came out to be, say, 5,000 watts, I could plug one of these in, I'd draw 220, or 2,200 would be fine. If I plugged two of them in, I'd be at 4,400 watts, still fine. But if I plugged three of them in, I'd be at 6,600 watts, which is over the 5,000, no longer fine. So that's how we work part B. So let's talk a bit about 21. Now, you know, I know I skipped a few of these, but a lot of these are very, very, very similar questions. In number 7, for example, real quick, it says in number 17, find the current that flows in a 90 watt bulb used at 120 volts. So for 17, write out power equals current times voltage, like I just did. They gave you a wattage and a voltage. You would solve for the current. In 18, very similar. 19 also similar. So I'm going to jump all the way to 21 here. Okay. 21, and I need to clear this space here. All right, what does it say here? It says a toaster operating at 120 volts uses 7.9 amps. What is the toaster's power output consumption? And again, I'm going to go ahead and draw a picture. I don't necessarily need it, but I love pictures. So this is going to represent my voltage, 120 volts. And again, a toaster draws, you know, your household power is what's called AC voltage, which technically has a different symbol. But again, we're going to talk about that later. It's not important for this particular problem. I'm just going to leave this the way it is. So 120 volts. Now the toaster, in the circuit diagram, we don't draw the actual, you know, we don't draw a toaster. We draw the effect of the toaster on the circuit. And the toaster has some electrical resistance, and that's what that symbol means. Right, so in my picture, and I think I forgot this in some of my previous ones, but my current would go this way. Remember, current always goes from higher potential to lower potential. Part A says, what is the toaster's power consumption? So power can be written a couple ways. One is current times voltage, or power equals current squared times resistance. And in this example, we're given a voltage and a current is given. In my problem, it says 7.9 amps. Yours might say something else. But there's your voltage, there's your current. That'll allow you to calculate the power. All right. Part B, where it says how much energy does this thing use in 2 minutes? So in order to calculate that, let's talk about what power is. Remember that power is equal to change in energy over change in time. And remember how it's defined, rate that energy is transferred. So if I know a power and a time, I can calculate a change in energy. So if I take the delta T and put it over here, this is going to be power times delta T. Take the power given in watts, or that you got from part A in watts, and then just multiply by your delta T given. Now in my example, it says 2 minutes. Remember that a watt is a joule per second. So this is delta T. You want to convert that to seconds and then multiply them. Part C, where it says, what is the total resistance of the heating wire, or the element wires? So there's a couple ways I think we can get at that. One is this. Remember, this is all in equipotential up to that point. So red to black is 120 volt potential. And as I look here, red to black. So we can use Ohm's law, V equals IR. Put the voltage here, the current we found earlier, and use it to calculate the resistance. Or we can look here, right? Power is equal to I squared times R. Somewhere, let's see, in part A, you calculated the power. That value would go here. And then the current is given in the problem. That value would go here, and then you can calculate R. So that should be enough here to get number 21 done. I'm going to call that good for this video. Hope it helps with these things. Have a great day.